Erythropoietin, a glycoprotein hormone having 34 kilodalton molecular weight, 10% secreted from hepatocytes of liver and 90% from the kidneys, is the master regulator of erythropoiesis. Previously, we discussed what is erythropoiesis, how erythropoiesis occurs in red bone marrow, and how the cells are sequestered into circulation. Today, we are going to more deeper and understand that how erythropoiesis is regulated by this hormone erythropoietin. So let's begin. Erythropoietin, as I told, it's a glycoprotein hormone of 34 kilodalton molecular weight. This hormone is secreted from liver, that is hepatocytes, and accounts for only 10% and carries out 15 to 20% of erythropoiesis in the routine life. That means the hepatic erythropoietin is not that important like the renal erythropoietin. It is secreted from kidneys and it accounts for 90%. A lot of controversies exist for the source of secretion from the kidney. People say it is from the tubular epithelial cells, but actually this is secreted from pericytes, which are surrounding the tubular epithelial cells. These are contractile cells, but as they are surrounding the endothelium, they are also having endothelial function. And here they are the major regulator of secretion of erythropoiesis, which carries out 70 to 80% of erythropoiesis. That means we can say that the major regulator of erythropoiesis, and it is secreted from the liver, it is secreted from the kidney, but kidney serves as the major source of secretion, and tubular pericytes are the major regulator and major source of secretion of this hormone. Erythropoietin is stimulated by hypoxia. This is the predominant factor which is known till date to be considered as the most important factor which stimulates the kidney, which stimulates the liver to secrete, and then it causes erythropoiesis in the red bone marrow. Hypoxia is a state where oxygen availability to the tissues is decreased. There are multiple reasons, maybe pulmonary disorders, maybe anemia, maybe hemorrhage, or any other disorder where the oxygen availability to the tissues fall. Tissues develop a sense of deprivation of oxygen, and this is known as hypoxia. This hypoxia is sensed, and this sensing is done by the sensors, and these sensors are present in the renal tubular pericytes. As a consequence, these renal pericytes, they secrete this erythropoietin. So mostly this erythropoietin which is secreted from the kidney will bring out the process of erythropoiesis. So what is the summary of discussion? Erythropoietin is the major regulator of erythropoiesis, first. Second, erythropoiesis is secreted from hepatic source and renal source, but the renal source is the dominant and the major. Hypoxia serves as the most important factor for regulation of erythropoietin secretion. Hypoxia of any reason leads to secretion of erythropoietin. Hormones like epinephrine, norepinephrine, and prostaglandins, these are also known to regulate the secretion of erythropoietin. That means they are also the other regulators which stimulate the erythropoietin release. Now, the last point, what actually erythropoietin brings out? How oxygen is being sensed, means hypoxia is sensed. How the erythropoietin hormone gene is undergoing the process of expression so that this erythropoietin is secreted. That is the point of discussion. The concept is, you can see this is the long bones. The end points are the RBM, the red bone marrow. From the red bone marrow, these are the PHPC cells, pluripotent hemopoietic stem cells, as we discussed last time. These PHSC cells, that is this erythroid series of cells, they will give rise to erythrocytes, and these erythrocytes undergoes a series as explained earlier, that is from the pro-erythroblast or from the word rubriblast to the immature just previous stage, that is reticulocyte to erythrocyte. So what the erythropoietin brings out? The erythropoietin which is secreted from, let it be here, the kidneys. Why it is secreted? It is secreted due to hypoxia. This erythropoietin acts here on the PHSC cells, on the pro-erythrolyte cells, and number of intermediate stages of RBC development, and lead ultimately to formation of erythrocytes. One of the fundamental application at high altitude, when a person moves to high altitude, which is more than 5400 meter above the sea level, then partial pressure of oxygen decreases and transient hypoxia starts developing. During this time, erythropoietin is secreted and it causes faster erythropoiesis. As a consequence, the circulating number of erythrocytes increases, and that we say as transient polycythemia. That means increase in the number of RBCs. But why this occurs? Now, because body is sensibly getting less amount of oxygen in the tissues, and the sensors in the kidney are sensing that body is developing hypoxia, and therefore this consequent mechanism of erythropoietin secretion occurs. Now we are coming to the most dynamic part of this lecture, that is the mystery behind the sensing of hypoxia. What actually happens? Because what you are seeing, that is the outcome, that is the physiological outcome. But what actually happens inside, that's known as the signaling, that's known as the cross communication or the crosstalk. So let's see how body senses it, what body carries out, what is the consequence, and what is the result. It's a beautiful interplay is there, and this is one of the most dynamic events, because our body almost replaces 1% of the RBCs every day. 1% of the RBCs are formed every day. That means it is coming around 30 trillions. So it's a huge number. So that means always there is cross-talk mechanisms are on, And as a consequence to this, our body is able to maintain a constancy in the number of RBCs so that RBC will carry adequate amount of oxygen and can remove carbon dioxide, consequence to which our body is well balanced or physiologically normal with respect to oxygen delivery, carbon dioxide removal. So what actually happens? Hypoxia, this is less partial pressure of oxygen and decreasing tissue availability of oxygen. Now the concept begins. Due to this reduction in tissue availability of oxygen, or you can say hypoxia, there is an induction of a factor that is known as hypoxia inducing factor, that is HIF. This is the role model. This hypoxia inducing factor is said to be the role model, which is said to be belonging to helix, loop, helix, heterodimer group of protein. This belongs to helix, loop, helix, heterodimer group of protein. Dimer group of protein, and this is secreted when the hypoxia is being sensed by the kidney sensors. During normal availability of oxygen, that is normoxia, when oxygen availability is normal, HIF, this HIF, it undergoes degradation. This is the point to be noted, that HI undergoes a degradation when the body is having normal supply of oxygen, normal availability of oxygen. When hypoxia is there, then this HIF is causing the erythropoietin secretion. Now there are three very important questions. How it undergoes a degradation during normoxia? How it is not going degradation during hypoxia? And how hypoxia is causing this HIF to secrete the erythropoietin? Now let's make a very important flow chart. Before that, let me tell you a few things, then I'll go. This HIF, it is having two forms, HIF alpha, HIF beta. This HIF is the inducible form. Point to be noted, inducible means during hypoxia, this is induced, this is formed. HIF beta, it is the constitutive form. That means always it is expressed and its level is not going to change with respect to the availability of oxygen, or you can say hypoxia or normoxia. That means this is constitutive, this is expressible. This HIF exists in three forms: HIF 1 alpha, HIF 2 alpha, HIF 3 alpha, three isomer forms. This HIF 2 alpha is the most important factor for the promotion of erythropoietin secretion and release. Now question arises, if you are saying that HIF 2 alpha is important, then what it brings out? How people came to know that this HIF alpha is the most important one, or 2 alpha is the most important one? Because deletion of this gene causes hypoxia-induced erythropoietin expression less or almost inhibited. If you delete this HIF 2 alpha particularly in the null models, then it is seen that anemia occurs. Circulating number of RBCs decrease. Hypoxia-stimulated erythropoiesis from renal pericytes, that also falls. So these experimental studies clearly justify that HIF2 alpha is the major inducer of hypoxia-mediated erythropoiesis. Now coming to a beautiful flowchart which will really justify what actually happens, and then this degradation is converted to its conservation, and thereafter this expression of the gene and secretion of the erythropoietin. Let's go for the master flowchart which will show how this HIF is regulating the process of secretion of erythropoietin. So I can draw like this: body state. This is the master flow chart. With respect to oxygen availability, we can define it as normoxia, that is physiological availability of oxygen is normal. And when I am using the word hypoxia, it means physiological availability of oxygen is less. So that is hypoxia. This HIF, that is, this point is very important because hypoxia inducing factor is always present, no doubt about that. But during normoxia, when normoxia is there, this HIF undergoes degradation, and this degradation occurs by what mechanism? That means during hypoxia, this HIF, it is conserved, means not degraded. This what we got from the previous one. Now question arises, why? The answer is this degradation is a proteasome mediated degradation, and this degradation is proteasome dependent or mediated. Now another question, how? If it is conserved and not degraded during hypoxia, then the last point which comes to the mind, what it carries out. What it carries out. What is the summary of this particular flowchart? During normal availability of oxygen, HIF undergoes proteasome dependent or mediated degradation. During hypoxia, this HIF is not degraded, but it carries out something. And what is that answer? It carries out transcription of erythropoietin hormone gene, and that leads to the secretion of erythropoietin from the renal pericytes. So the message is very clear. We are now understanding that why HIF is not able to do anything or no role during the time of anemia, during the time of normoxia, but during hypoxia, this HIF is mediating this erythropoietin secretion, and which brings out erythropoiesis. So now two questions are there: how proteasome dependent, how it is not degraded, what it brings out. So let's make two more flowcharts to show the condition during normoxia and the condition during hypoxia. Let's see. This process is really dynamic because it occurs through the sensing mechanism of the kidney tubular pericyte cells, which are the real sensors of this oxygen, and thereafter this HIF is critically cross-talking with them to bring out the process. Let's draw that normoxia first. The body is having normoxia. What I told? This HIF is having two types rather. I can HIF alpha, HIF beta. HIF alpha is the inducible form. As I already explained, HIF beta is the constitutive form, as I told earlier. This HIF alpha is having the proline residue. This proline residue undergoes hydroxylation. That is that key process, hydroxylation. That means the OH group is added during normoxia, I am saying. Once it undergoes hydroxylation, then at the proline residue, it is forms a complex with a protein, and this protein makes it to be undergo ubiquitation. This ubiquitation is the process which will lead to proteasome dependent degradation. That means what I am saying, once again I am repeating, this HIF alpha is having the proline residue. At the proline residue, it undergoes the hydroxylation. Once it undergoes hydroxylation, then it binds with a very complex protein. That is, now I am making you clear, this protein is known as VHL. We'll see what is that VHL. Once it binds with the VHL, this complex now undergoes ubiquitination, and after ubiquitination is over, then it undergoes proteasome dependent degradation. That means this HIF is now not functional because HIF beta cannot, that is constitutive, will become non-functional. It has no role. Now the protein, this VHL, that's known as 1-hyper-Lindau. This is the name of the scientist, Lindau. This is the specialized protein, short form, that is known as VHL. This carries out a complex ligation process that leads to this ubiquitination and followed by the proteasome dependent degradation. So that's why during normoxia, HIF undergoes degradation. So this is the point to be noted. So this is the third flow chart of this lecture, where I want to convey you that during normoxia, this HIF has no role in the process of erythropoiesis as it undergoes degradation. Now coming to the next one, where we will justify actually what happens during hypoxia. Another master flow chart, and this will complete whole of our concept that what actually happens and by virtue of which this HIF becomes functional and the circulating count of RBCs will increase to maintain the deficient oxygen supply to sufficient oxygen supply. So let's see how it carries out. Hypoxia. This causes this inhibition of, this is the master point, inhibition of hydroxylation of proline. And once this hydroxylation of the proline residue is inhibited, it cannot undergo, that means failure of ubiquitination, and once ubiquitination is failed, it is not degraded. This is the point. This is not degraded. Here, now this inhibition will lead to this two form, HIF alpha, HIF beta. This HIF alpha has three subunits, HIF 1 alpha, HIF 2 alpha, HIF 3 alpha. This one is important for us, this one. And this HIF beta, this HIF 2 alpha, now they will combine. That is the dimerization. Once HIF 2 alpha and HIF beta dimerize, they enter that complex, that dimerized complex now enters nucleus. Once they enter the nucleus, they bind to, that complex binds to hormone response element of erythropoietin gene. This hormone response element of erythropoietin gene undergoes transcription. This transcription is followed further by the translation, which leads to the erythropoietin protein to be secreted, that is secretion. And once this erythropoietin gene is transcribed, its expression is increased. So altogether, this leads to increase in the release of erythropoietin. So this is the whole sole mechanism of the hypoxia dependent HIF functionality and secretion of the erythropoietin hormone from the renal pericytes. And what is the consequence? Now this erythropoietin will bring out the erythropoiesis. That's what we require. So this is the compensatory mechanism which occurs in the body. It is so important to know that body sensing mechanisms are very active. Body tries to sense the deficiency so that physiologically it can fulfill, and compensatory mechanisms will occur. If any stage these compensatory mechanisms are failed, then sensing mechanisms also failed, or vice versa. Crosstalk mechanism, if at any stage is stopping, then hypoxia will still remain as hypoxia. All these mechanisms, what is being explained, they are trying to maintain the physiological levels in and around, means within physiological limits. If I can conclude this one, then I can draw another summarizing flowchart which will summarize the entire concept, and then we'll go to the concluding flowchart of this class. So this one can be summarized like this. Hypoxia. This is another master flowchart. Decrease oxygen availability, HIF alpha stabilization, then hormone response element of the erythropoietin transcription, as I explained, and after that this erythropoietin is secreted more. This erythropoietin, by the blood, it will go to the red bone marrow and it will stimulate the pluripotent hemopoietic stem cells, those which are going to release the pro-erythroblast cells, fastens the mechanism of erythrocyte stages. Without reticulocyte stage, it cannot go to erythrocytes, so reticulocyte stage also becomes faster, and then it converts into erythrocyte. Once erythropoietin is increased, circulating number of erythrocytes also increase. That means the carrying capacity of oxygen also increased, and this causes what is the consequence? This causes hypoxia to converted into normoxia. So this is the total science behind that. So whenever body suffers from any transient degree of hypoxia, this mechanism operates. The key factor here is the HIF alpha. HIF beta is constitutive, so that's why its role is said to be less important. But of course, without the dimerization of HIF alpha and HIF beta, there will be no transcription of erythropoietin hormone gene, and of course erythropoietin will not be secreted. So during anemia, high altitude, any bleeding disorders, hemorrhage, pulmonary dysfunctions, whenever the body suffers from any conditions of hypoxia, any toxemic states where hypoxia develops, then this sensing mechanism of the body develops this mechanism, and altogether this mechanism will lead to a physiological adjustment inside the body to maintain normal supply of oxygen. So that's why in the ancient past, from 90s to 2000, even today also, the classic athletes, they use this erythropoietin as a doping hormone. They use it as a drug for enhancement of the performance. I should not say it's a drug, it's actually hormone, but they take before a particular game to enhance their performance, as erythropoietin serves as a potential stimulant of erythropoiesis. If before performance the circulating number of erythrocytes will increase, then it will obviously increase the carrying capacity of oxygen in the per unit flow of the blood into the muscles. Thereby, they will provide oxygen in surplus quantities. Aerobic state will almost maintained and anaerobic state will easily be avoided, but it occurs, and thereby the performance enhancement occurs. So with this, we are coming to a very big conclusion that hypoxia is the regulator of HIF factor action. And before stopping, I can say one more point of HIF. It helps or promotes angiogenesis. It promotes cell division. It promotes cell differentiation. It promotes cell metabolism. So these are also some of the functions, and it also, I can add another one, it also adds energy homeostasis. That means so many important functions are there for this HIF alpha. Besides here, this erythropoietin, it also brings out number of activities. So that's why it is said to be a master molecule during the time of hypoxia. Let's conclude this class with a master flowchart which is following after this. So this is the master flowchart, hypoxia, inhibition of hydroxylation of proline residues of HIF, particularly alpha. This is one important consequence is inhibition of proteasome mediated degradation. What happens thereafter? Now once this is inhibited, HIF2 alpha binds with HIF beta, enters nucleus and of nucleus of renal pericytes, stimulates the secretion of erythropoietin, as I told earlier, due to the expression of the erythropoietin synthesizing and secreting gene. Now the point, here it comes the important point. Erythropoietin comes to the red bone marrow. It acts on three parts. It acts on pluripotent hemopoietic stem cells, as we discussed, pro-erythroblasts, what we talked about as rubriblasts. It will increase the conversion of PEH-SC cell to pro-erythroblast or rubriblast, which are very rapidly converted into reticulocyte, the stage where reticulum is present, nucleus has already disappeared, hemoglobin is quantifiable amount, means very good amount, which goes and ultimately mature to form erythrocytes. So what happened? Now there is increase in the erythrocyte count. Once this is increased, there is increased supply of oxygen. Once there is increased supply of oxygen, then gradually normoxia develops. And once normoxia develops, now you can understand, once normoxia develops, this inhibition, what I have written here, this inhibition, now it will stop. That means this normoxia will now cause the HIF alpha degradation. So this is known as the homeostatic regulation. That means crosstalk is going on. Cells are sensing. When they are sensing hypoxia, they are doing erythropoiesis. When they are not sensing, then automatically that is evacuated and that is being destroyed or degraded. And now the reverse process will start, as I told, hydroxylation of the proline residues, and thereafter the continuous processes will go on. So with this lecture justifies that how erythropoietin, hypoxia and the renal pericytes play an important role. So in the next lecture, we will come and discuss what are the other factors which are affecting the erythropoiesis, like hormones, growth factors, vitamins, minerals, cofactors, exercise, or whatever. There are multiple factors are there which are regulating that process. Today, I tried my level best to say you the molecular signaling processes associated with the sensing of oxygen and secretion of the erythropoietin. So keep learning. Thank you very much for your time. Go through this lecture, have some questions. If you have, write it down for me so that I can address in my coming lecture. With this, stay tuned for the next lecture. Have a wonderful time ahead.